Hey guys, today we're going to be learning about optimization. Now, optimization is the process of which you are either maximizing or minimizing some type of quantity that may be subject to constraints, meaning limiting information. Some examples may be maximizing profits, minimizing costs, and mainly for us, we're going to be maximizing area or volume or minimizing these types of quantities. Now, I put here a general approach to solving these optimization problems. The main issue with optimization is that sometimes you may have too many variables, which is why a constraint is usually useful, or it's always useful. So first, with all of these problems, you're going to determine what is the quantity that you need to maximize or minimize. Then you're going to write a primary equation that represents what it is that you're trying to optimize. If the primary equation has more than one variable, then a secondary equation has to be written. And this secondary equation is usually written from the constraint that is given in the problem. Once you have that, the constraint is usually in one variable that then you can plug in to the equation that you're trying to maximize or minimize, and then find the derivative and check that it is indeed a maximum or a minimum and answer the question. So let's see a couple of basic examples. So this first one says, what is the minimum product you can achieve from two real numbers where one of them is less than twice the other? So what we're trying to minimize is a product of some two numbers that we don't know. So I'm going to say xy. This is what we are trying to minimize. Now we are given a constraint, which is where one of them is 3 less than twice the other. So let's just say that y, right, it doesn't matter which variable you choose. You can also have used a and b. I mean, it does not matter since we're just trying to solve for these. So we'll say that y is 3 less than twice the other, so 2x minus 3. Now this is my constraint. So since I have this as y, what I do is I plug it in here. So x times y, which is 2x minus 3. Distribute, we get 2x squared minus 3x. This is what I want to minimize. So now what I'm going to do is I'm going to find the derivative, which is 4x minus 3. Now remember, if you're looking for a minimum or a maximum, that is when the derivative is equal to 0. And we have to find that critical number, which for this one, you would just add the 3 divided by the 4. So my critical number would be x is equal to 3 over 4. Now, since this is the only critical number, this must mean that this is indeed the minimum. But we always want to just verify through our sign analysis here. So this is my derivative. If I plug in 0, 0 minus 3 is a negative number. And if I plug in 1, 4 minus 3 is positive. So this is indeed a minimum. So we have what x is equal to, but I need to know what y is so I can get the minimum product. But luckily, I have this equation here for y. So we just plug in the 3 over 4 to solve for y. So y is equal to 2 times x, which is 3 over 4, minus 3. 2 times 3 over 4 is 6 over 4, which can be simplified to 3 over 2, minus 3, I'm going to have to put this over 2, meaning 6 over 2, which gives me that y is equal to negative 3 over 2. So to get the minimum product, I plug in what I got for x and what I got for y. So 3 over 4 times negative 3 over 2 gives me a minimum of negative 9 over 8. Let's look at this next question. A box is to be built from a rectangular piece of cardboard that is 25 centimeters wide and 40 centimeters long by cutting out a square from each corner and bending up the sides. Find the size of the corner square that will produce a container with a maximum volume. So I'm going to draw a picture so you can kind of understand this a little better. Here is my rectangle. We are going to cut a square piece from every corner. So this would be x, and this is x, since squares all have equal sides. Now, if we to cut these pieces and then fold up, let's say this is gone, this is gone, this is gone, and this is gone. When you fold up the sides, you get a box, where this right here, what I have here in the dotted line, would be the base of that box. So now we're trying to maximize the volume, right? But what we're trying to solve for here is x. But either way, that's the optimization here, is we're maxing volume. Now volume, we know, is length times width times height. We are told that the width of this rectangle is 25 and the length here is 40. Now the length of the box is not the 40 because we had to cut these sides. So if you think about what the length would be, it would be 40 minus this x minus this x. So the length is 40 minus 2x. Same concept for the width. The width is the 25, but minus this x and this x. So 25 minus 2x. Now the height of the box, if I fold up the side, right, the height is this. That's your height of the box. So the height would just be x. So now this is my equation. I want to solve for x. It only has one variable, so that's why we weren't given a constraint, because we don't need one. So now what I'm going to do is we're going to multiply everything out, find the derivative, and get that critical number. If you multiply, right, 40 minus 2x times 25 minus 2x, that would give us, what is that, 10,000 minus 80x minus 50x plus 4x squared, and then times the x. We can combine these like terms. I'm just going to write this in standard form as well. So this is 4x squared minus 130x plus 1000 times x, which gives me my equation for volume, which is 4x to the third minus 130x squared plus 1000x. Now let's get the derivative, which is going to equal to 12x squared minus 260x plus 1000. All of these terms here are divisible by 4, so when I make this equal to 0, I am going to factor out the 4, which would give me 3x squared minus 65x plus 250. We have to make this quadratic equal to 0, and you can do that in either two ways. You can either use a quadratic formula, or we can use the AC method to factor it, which is the route that I'm going to take. So first I'm just going to get rid of this 4, because regardless it's not going to affect our answer, because 0 divided by anything is still 4. So I'm going to work with this here. AC is 3 times 250, so what is that? 750. And the two numbers that would multiply to give me 750, positive 750, and add to give me negative 65 is negative 15 and negative 50. So I'm going to rewrite this quadratic up here, so 3x squared, using those two numbers for b. So minus 15x minus 50x plus 250. Factor by grouping. These two terms have a 3x in common, leaving me with x minus 5. These two terms, I can factor out a negative 50 because of this minus here, which would leave me with x minus 5. When you're factoring by grouping, as long as these are the same, that's one of your factors. And what's left over is the other factor. And when you solve for your critical numbers, we get that x is equal to 5. And here we would add the 50 divided by 3, so 50 over 3. Now, since we have two critical numbers, that means that we need to figure out which one of these is the maximum. So we're going to put these on our number line. This is my derivative factored out. If I plug in 0, I get a negative times a negative, which is positive. If I plug in 6, I get a positive times a negative, which is negative. And if I plug in, let's say, 25, I get positive times a positive, so positive. So my maximum here is when x is equal to 5. And what we were solving for here is the size of the corner square, which the corner square is x, right? Or those are your dimensions, x by x. So the size of my corner square would be 5 centimeters by 5 centimeters. Whenever you're giving dimensions of a 2D figure, you give the length and the width. If it's a 3D figure, you give the length, the width, and the height. Let's go on to another example. And that's all we're going to do with this lesson, is go through lots of different kinds of examples. We have here a manufacturer wants to design an open box having a square base and a surface area of 108 square inches. What dimensions will produce a box with a maximum volume? Okay, so first I'm going to draw a box. Now it's an open container, so there is no lid, right? This here is empty. This is my base. And it says that it has a square base. So that means that this is x, and this here is also x. The height, however, I don't know. We call that y, since we're not sure if the height is also the same. So what we are doing here is we're maximizing the volume, and we also want to get the dimensions. So volume is going to equal to length times width times height. So x times y, giving me x squared y. Now the constraint here is that the surface area has to be 108 square inches. Now the surface area of any figure is when you get the area of all of the sides and you add it together. So since this is a square base, remember the area of all of these sides is just length times width, since every side here is either a square or a rectangle. Now the base is a square, so that means that the area is x times x, so x squared. Plus, all of these sides here are rectangles, which have a base of x and a height of y. So the area of this rectangle, of this rectangle, of this one here, and this one here is all the same, which is 4, because there's 4 of them, base times height. It has an open lid, so we don't have to worry about the surface area of the top of this box. So that's the area, and it has to equal to 108. When you have a constraint that also has two variables, what we do is we solve for one of those variables. Now, it doesn't necessarily matter which one you choose to solve for, but in this case, since we have x squared plus 4xy, I'm going to solve for y, since the only variable that I can actually isolate. So we're going to subtract the x squared. So 4xy is equal to negative x squared plus 108. And then divide by 4x. So this is y. So I'm going to write that over here. Y is equal to negative x squared plus 108 divided by 4x. Now what I do with this is I take it and I'm going to plug it into my equation for volume. So volume is equal to x squared times all of y, which is negative x squared, plus 108 all over 4. Now this, 4x. Now this x squared and this x can cancel. leaving me with only one x here. So now I can distribute the x, leaving me with volume is equal to negative x to the third plus 108 all over 4. And what I'm going to do now is I'm going to put everything individually over 4, which is negative x to the third over 4 plus 27. And I did that just to make it easier on myself now when I take the derivative. So remember, for these optimization problems, what did we just do? We got the equation we needed to maximize. We wrote down the constraint. We solved for a variable. And then whenever you do that, you take it back into the equation that you're maximizing and you plug it in. So that way, the equation that you're trying to maximize is in one variable. Now we have our equation for volume. Now we find the derivative. So v prime is going to equal to negative 3x squared over 4. That's it. Oh wait, isn't this x? Sorry. So plus 27. And now we make this equal to 0. So let's solve for x. So I'm just going to move on over here. So we can subtract the 27. So negative 3 over 4x squared is equal to negative 27. I'm going to multiply by the reciprocal of this fraction so I can cancel it out. So multiply by negative 4 over 3. The negatives will cancel. 27 divided by 3 is 9. And then 9 times 4 is 36. So square root both sides. We get that x is equal to plus or minus 6. Now remember that what we're solving for here are dimensions. Okay, so dimensions cannot be negative. So actually, the only x value that is valid is the positive 6. And this is the base of your box here. So we want to verify that this is indeed a maximum. So we go to the derivative equation. If you plug in 0, you would get 0 plus 27, which is a positive. And if I plug in 7, then this would be one large number, and it's negative, plus 27, so negative. So this is indeed a maximum. Now we have x. Now we wanted the dimensions, right? So we have the x value, but we need the y. But remember that I have the equation here for y. So y is equal to negative x squared plus 108 all over 4 times x. Negative 6 squared is negative 36 plus 108 divided by 24. Negative 36 plus 108 is 72. And 72 divided by 24 is 3. So this is the value of y. So my dimensions, remember we have to give now the 3 dimensions, the length, the width, and the height, would be the 6 inches by 6 inches by the 3 inches for the height. And the max volume is when you multiply the length times width times height. So 6 times 6, which is 36, times 3 is coincidentally also 108 cubic inches. Let's look at another example. Here we are minimizing area. A rectangular page is to contain 24 square inches of print. The margins at the top and the bottom of the page are to be 1.5 inches, and the margins to the left and right are to be 1 inch. What dimensions, or what should the dimensions of the page be so that the least amount of paper is used? Whenever you're given a question where it's asking about the least amount of anything that is used, what they're talking about is to minimize the area, the surface area. So that's what we have here. So let's just draw a picture so we get a clear idea of what we're looking for. We have our sheet of paper. Here we have the print, which is 24 square inches. I don't know the measurements of this, so I'll call this X and this Y. The margins here and here from the top and bottom are 1.5. and to the left and the right are 1 and 1. So now, in order to minimize the area of the page, remember the area is going to be this. So this, all of that would be x, right, because of this here, plus the margins, so 2. And this here would be the y, plus 1.5 plus 1.5, so y plus 3. So the area is x plus 2, y plus 3. Now we are told that the print part of the page is 24 square inches. So that means that the area there is 24. So we can solve for either x or y. I'm going to choose to solve for y. So y is equal to 24 over x. So now I'm going to plug that into the equation that I am trying to minimize. So area is going to equal to x plus 2 times 24 over x plus 3. Distribute, and we get 24, because the x's will cancel, plus 3x plus 48 over x plus 6. Now remember that I need to find the derivative of this. So I'm going to rewrite this as 30 plus 3x plus 48 x to the negative 1. So now the derivative is going to be 3 minus 48 x to the negative 2, which is 3 minus 48 over x squared. So this is my derivative. I make it equal to 0, and now we're going to solve for those critical numbers. First, we can subtract the 3 over, so I'm going to do that over here. So negative 48 over x squared is equal to negative 3. Multiply the x squared to both sides. We get negative 48 is equal to negative 3x squared, since we don't want the x squared in the denominator. Divide negative 3. We get x squared is equal to 16. And then square root, we get x is equal to 4. Remember, not plus or minus 4, just the positive 4, since these are dimensions. So, let's confirm that this is indeed a minimum. If I plug in, let's say, 1, I get 3 minus 48, which is a negative. And let's say if I plug in 5, I get 3 minus 48 over 25, which is a fraction, so positive. So this is indeed a minimum. So x is equal to 4, and we want to figure out the dimensions. So now I also need to figure out what y is equal to. Y is equal to 24 divided by x, which is 4, so 6. So the dimensions, remember, of the page, right, x plus 2 would be 4 plus 2, so 6. And then y plus 3, which is 6, plus 3 is 9. So the dimensions of my page are 6 inches by 9 inches.